if you type like just a single uppercase letter R into a chatbot, the system sees entirely different math than if you typed a lowercase r. To us, I mean, it's just grammar, right? Maybe it's the start of a sentence versus the middle of a word. But to an AI, those two letters, they exist in totally different mathematical universes.
Right, and that disconnect right there is exactly why interacting with these systems so often feels like casting spells. We expect them to read and write like humans do, but they are fundamentally processing numbers. The underlying mechanics are just completely alien to how human language actually works.
Yeah, which is wild to think about. Welcome to the deep dive, everyone. Our mission today is to completely demystify the black box of artificial intelligence. We interact with these models every single day, but those few seconds between, typing a prompt and getting an articulate essay back, for most people, that's just pure magic.
And we are tearing that box open today.
Exactly. We're looking at the foundational architecture, the exact vocabulary and concepts driving the entire AI economy right now. And we've got an incredible stack of technical sources to guide us today.
We really do. We're pulling from foundational research like the famous 2017 Attention is All You Need paper, the landmark 2020 RAG Paper Plus technical documentation from Hugging Face, OpenAI, Llama Index, and even the latest prompting guides and pricing structures for Anthropic's Claude 5 models.
It's a goldmine. And this matters directly to you, the listener, whether you are building your own AI apps, managing an enterprise team, or just insanely curious about how a chatbot actually thinks. This deep dive will give you the framework you need to understand this whole new world. So, okay, let's unpack this.
Let's do it.
Before a system can generate a response, it obviously has to read your prompt. But as we established, an AI doesn't read English or Spanish or Python code. It only digests numbers. So every piece of text we feed it has to be converted into numerical data. And this brings us to the invisible currency of AI, the token.
The token, yeah, it is the fundamental unit of compute in this space. And it's really helpful to think of tokens not as full words, but as chunks of information.
Like syllables, almost.
Sort of, yeah. A good rule of thumb, and this comes straight from the OpenAI documentation, is that for English text, one token is roughly 4 characters, or about 3/4 of a standard word.
Okay, so 100 tokens gives you about 75 words.
Exactly. But the way words are sliced into these tokens, it isn't just arbitrary.
Right, because if we just assigned a unique number to every single word in the English language, plus every variation like run, runs, running, the model's internal dictionary would be impossibly huge, right?
It would be unmanageable. And beyond just the size, it would have no inherent way of knowing that those 3 words are even related to each other.
Okay, so how do they fix that?
The industry uses a technique called subword tokenization, which Hugging Face explains really well in their docs. Basically, the system keeps common words whole, but it breaks rare or complex words down into meaningful fragments.
Meaningful fragments. Can you give an example of that?
Sure, take a word like annoyingly.
Okay.
It's relatively rare in a training data set compared to just annoying. So the tokenizer splits it into 2 tokens, annoying and loying.
Oh, wow. That feels like a brilliant structural compromise. By breaking it into pieces, the AI gets to keep the core semantic meaning annoying, but it also retains the grammatical function of the suffix loy.
Right, and it prevents the model from just hitting a wall. If an AI encounters text it simply doesn't have a number for, it has to output an unknown or a bracketed UNK token.
And you don't want a bunch of unknown tokens flying around.
No, it ruins the output. So subword tokenization keeps the vocabulary size manageable, usually around 50,000 to maybe 100,000 unique tokens, while ensuring it can assemble almost any word it ever encounters from those pieces.
But it's incredibly sensitive to formatting too, isn't it? Going back to our example with the letter R from the intro.
Oh, heavily sensitive.
Let's look at the word red, like the color. To a human, red is a color regardless of where it sits in a sentence. But the tokenizer captures the structural environment of the text, right?
It does. It captures the spacing, the capitalization, everything.
Yeah, so a lowercase red with a space before it gets assigned one specific numerical ID, let's say 2266. But an uppercase red with a leading space gets a completely different ID, maybe 2297.
Yep.
And red at the very beginning of a prompt with no space at all. That's like 778.
Because structurally, a word at the beginning of a sentence serves a different grammatical purpose than a word buried in the middle of one. The model needs those distinct numerical IDs to track the syntax and context.
Okay, so if tokens are essentially a box of numbered Lego bricks, The AI takes my prompt and smashes it into these little modular pieces.
That's a great way to visualize it.
But I have a serious pushback here. If the AI is just staring at a list of numerical Lego bricks, how on earth does it understand, like, sarcasm or irony or complex logical instructions? I mean, a pile of numbered bricks doesn't magically create intelligence just because you chop the words up efficiently.
That is the multi-billion-dollar question. And frankly, the processing of those tokens is the entire basis of the modern AI economy. I mean, AI companies charge developers based entirely on token economics.
Right, the API costs.
Exactly. You pay a fraction of a cent for every input token you upload and a slightly higher rate for every output token the model generates, because every single token requires physical electricity and compute power to process.
So to get from a pile of bricks to actual comprehension, we need something else.
We need an architecture that can map the relationships between those numbers.
Which means we need to talk about the transformer.
We definitely do. So in 2017, a team of researchers at Google published a paper called "Attention is All You Need."
Such a great title.
It really is, and it is arguably the most important computer science paper of the last decade. It introduced the transformer architecture, which fundamentally changed how machines process those tokenized Lego bricks.
Let's look at how things worked before that 2017 paper, just for contrast. We had systems called recurrent neural networks, or RNNs.
Right, the old guard.
Yeah, and the limitation with RNNs is that they read text sequentially, left to right, one single word at a time. It's almost like a human trying to read a book through a tiny, narrow straw.
The sequential bottleneck was just brutal. If an RNN was reading a long paragraph and needed to understand a word at the very end, it had to actively hold on to the memory of every single word that came before it, step by step by step.
Which I imagine gets overwhelming fast.
It does. By the time it reached the end of a long sentence, it often just forgot what the beginning was even about. The longer the context, the more the network's understanding degraded.
But the transformer throws that left-to-right rule completely out the window, right?
Oh, yeah.
Using a mechanism called self-attention.
Exactly.
So instead of looking through a tiny straw, it steps back and looks at the entire page of text all at once.
It processes everything in parallel. The self-attention mechanism performs a small, constant series of mathematical operations to directly model the relationships between all the words in a sequence simultaneously.
The source notes actually have a perfect example of how this maps meaning. Take the sentence. I arrived at the bank after crossing the river.
Classic example.
Yeah, so when the model processes the token for bank, the attention mechanism instantly calculates a mathematical relationship between bank and every other token in the sentence. And it notices a very strong statistical link to the word river.
Right, and through that high attention score, the model immediately knows we are talking about a muddy shoreline, not a financial institution where you go to deposit a check.
Doesn't have to wait to read the rest of the sentence to figure it out.
No, the context is baked into the mathematical weights instantly.
It's basically mapping a web of invisible strings between all the Lego bricks, pulling the related concepts closer together. And it handles incredibly subtle linguistic puzzles this way, too. Like, the classic problem in AI is called coreference resolution.
Oh, yeah. Pronouns.
Right, basically figuring out what a pronoun is actually referring to.
Pronouns are historically an absolute nightmare for computers. I mean, think about the sentence, the animal didn't cross the street because it was too tired, versus the animal didn't cross the street because it was too wide.
So the first sentence, it refers to the animal, but in the second sentence, it is the street.
Exactly. For a human, common sense just tells us streets don't get tired, but a machine doesn't have common sense.
Right.
The transformer solves this by distributing those attention weights across the entire sentence in a single step. It calculates that tired strongly connects to animal, and wide strongly connects to street.
And this is totally critical for translation, too, isn't it? Because in languages like French or German, the gender of the translated pronoun changes entirely depending on what specific noun it refers to.
Yep. If it doesn't know what it refers to, it can't translate the sentence grammatically. The transformer fixes that.
Okay, so the transformer can look at the whole page at once, calculate all these relationships simultaneously, and understand the context flawlessly. But, and here's my pushback, that raises an obvious limitation.
What's that?
If it's looking at the whole page, how big is the page? Like, why can't I just upload my company's entire 10 million line software code base or a 5,000-page legal discovery file and just let it look at all of that at once?
What's fascinating here is that you've just hit on the concept of the context window.
Context window.
Right. The transformer's working memory is finite. Think of it like the RAM on your laptop. Even the absolute most advanced models today might have a context window of maybe a couple 100,000 tokens.
Which is a lot, but not 10 million lines of code.
Not even close. If you try to force a 30 million line Linux kernel into a space designed for a short novel, it physically will not fit. The matrix multiplication required to calculate attention across that many tokens simultaneously, it would require an impossible amount of compute power.
So if the model's brain is too small to hold the entire encyclopedia at once, we need a bridge to external data.
Exactly. We need a way to find exactly the right paragraph from that huge code base and hand only that specific paragraph to the transformer.
Okay, and that bridge is what we call retrieval augmented generation, universally known as RAG.
RAG, introduced in a landmark 2020 paper by Patrick Lewis and his team. It fundamentally shifted how the industry approaches AI knowledge. Rather than trying to force a model to somehow memorize every fact in the world during its training, we just give it a search engine.
The architecture breaks this into two distinct types of memory, right? You have the model's internal parametric memory, which is the linguistic patterns, the logic, and basic facts baked into its neural weights during the months it spent training.
Right, like a pre-trained BART model.
Yeah. And then you have non-parametric memory, which is an external database. That could be your private HR manuals, a massive database of medical journals, or just a folder of PDFs sitting on your hard drive.
The magic of RAG is how it connects the two using something called embeddings. Remember those Lego bricks we talked about earlier? Embeddings take those chunks of text and plot them in a multidimensional mathematical space.
Okay, let's slow down on that for a second, because multidimensional mathematical space is a pretty dense phrase. How does that actually work in practice?
Okay, imagine a massive 3D coordinate system, like a graph you draw in high school algebra, but instead of just an X, Y, and Z axis, it has thousands of axes.
Okay, thousands of axes. I'm picturing a crazy 3D grid.
Right. The embedding model evaluates a paragraph of text and assigns it a set of coordinates in this huge space based entirely on its meaning. Concepts that are semantically similar are plotted physically closer together.
So the coordinate for the word dog is placed very close to the coordinate for wolf, but incredibly far away from the coordinate for, like, toaster.
Exactly. You got it. So if I have a 500-page manual, the RE system first does something called chunking. It chops the manual into hundreds of small paragraphs. Then it runs them through an embedding model, precisely. Then, when a user types a question into the prompt, the system takes that question, runs it through the exact same embedding model, and plots the question as a coordinate, too.
Oh, I see where this is going.
Yeah. The search function simply looks for the chunks of the manual that are physically closest to the question in that mathematical space.
It just measures the distance. It scoops up the closest chunks, drops them into the transformer's temporary context window, and says, hey, answer the user's question using this specific information.
That's RAG in a nutshell.
It's essentially taking an open book test. You don't need to memorize the encyclopedia. You just need a really good index to find the right paragraph before you write your answer.
And this is exactly why developer frameworks like Llama Index are so crucial right now. Developers use these tools to build complex RAG pipelines that automate this entire process, connecting raw, unstructured data sources like PDFs or SQL databases directly to the reasoning engine of the LLM.
Okay, but this introduces a new ceiling, doesn't it? Fetching a single paragraph to answer a single question is great for a customer service chatbot. But what happens when the task isn't just answering a single question?
What do you mean?
Well, what if you want the AI to do a multi-day project? Let's say you tell it, read these 50 financial reports, write a Python script to analyze the revenue trends, debug any errors in your code, and generate a final slide deck. An open book test architecture isn't enough for that.
No, it's not. And you are outlining the exact transition happening in the tech world at this very moment.
Right.
We are moving away from simple reactive Q&A chatbots and moving towards autonomous agents.
Agents.
Yes. When you combine the sophisticated token processing of a transformer with the vast external memory of our ARB pipeline, you get the foundation for today's enterprise-grade autonomous models. Specifically, models like Anthropic's Claude Fable 5.
Right. And the architectural leap from older models like Opus 4.8 to something like Fable 5 or Mythos 5 is focused entirely on sustained long-horizon autonomy.
Older models would just lose the plot if you gave them a multi-step, multi-day task. They'd write a script, hit an error, and just stop and wait for you to fix it.
But Fable 5 doesn't stop.
No. Fable 5 is engineered for perfect first-shot correctness on highly complex problems. It can maintain its logical train of thought across hundreds of sequential steps without a human holding its hand.
Part of that autonomy comes from its expanded toolset, right?
Right.
The documentation highlights its advanced vision capabilities, specifically its native ability to use bash and crop tools.
That's a huge distinction. Bash tools mean the AI literally has access to a command line interface.
Meaning it can type commands just like a human developer.
Exactly. It can execute code, navigate a file system, and read the resulting error logs itself. And the crop tools mean that if you hand it a massive, noisy image, say a cluttered server architecture diagram, it doesn't just passively look at the whole thing and get confused.
It acts on it.
It actively crops and zooms in on specific parts of the image to read the fine print all on its own.
Here's where it gets really interesting for the people actually paying the bills, though. With a model this autonomous, you control it using effort settings.
Right.
The new effort parameters.
Yeah, you can set the effort to low, medium, high, or axe high. But if you set it to axe, the model will deliberately loop on a problem. It will gather external context, write a draft, verify its own work, spot a flaw, and rewrite it entirely before ever showing you the final result.
Which yields incredibly rigorous, accurate output.
But, and here's my pushback on this, doesn't setting X high effort just give the AI a blank check to burn through my token budget by over-explaining things to itself?
Yes, and that is a major trap for developers. Remember our discussion on token economics?
Yep, you pay for every output token.
Right. Every time that model loops, reads, and rewrites in the background, it is burning through output tokens. A task that might cost you 2 cents on low effort could cost you $1 on X high effort because of how much invisible compute it used to verify its own work. That actually brings up a wild quirk in the Fable 5 documentation. Because the model is so eager to be thorough, if you don't give it explicit constraints on a high-effort setting, it goes completely overboard.
Oh, it really does.
It starts creating unrequested defensive Git branch backups of your code or drafting contingency plans you didn't even ask for. It's like having an over-caffeinated intern.
It genuinely just wants to solve every possible edge case. But from an engineering perspective, letting it run wild is a terrible idea. In fact, developer guidelines from Lamy Index and Claude explicitly warn against asking these autonomous models to, quote, show their work or echo their internal reasoning out loud in the final response.
Wait, really? Why wouldn't I want to see its thought process? If it's doing a multi-day task, I feel like I'd want a log of everything it thought about.
There are two main reasons. First, as we just said, asking it to print its internal monologue wastes a massive amount of output tokens. You are literally paying it to talk to itself.
Okay, fair. That gets expensive.
But second, and actually more importantly, it triggers the model's safety classifiers.
Wait, how does explaining its math trigger a safety warning?
Because models like Fable 5 are incredibly capable at things like cybersecurity and biological research.
Oh, I see.
Yeah, so if you force the model to explicitly narrate its deep implementation details for, say, a complex networking script, the safety guardrails scanning the output might interpret that detailed narration as a malicious hacking attempt.
Wow.
The classifiers will just panic and either degrade the quality of the response or refuse the prompt entirely.
So what's the workaround then? How do you monitor an agent on a 3-day run without breaking it or triggering a safety alarm?
Developers build in a specific send-to-user tool.
Send-to-user.
Right. Fable 5 can actually spin up parallel subagents, essentially dispatching multiple mini versions of itself to tackle different parts of your task simultaneously. If one of those subagents hits a wall and actually needs human permission, it uses the send-to-user tool to ping you with a specific question, wait for your reply, and then fold your answer back into its context without dropping the whole multi-day run.
Ah, so you rely on its internal reasoning and only surface the exact updates you need.
Exactly. It keeps the token cost down and avoids the safety tripwires.
So to recap this incredible journey for everyone listening, we started with the raw numerical currency of tokens. We saw how the transformer architecture stopped reading through a tiny straw and looked at the whole page, mapping meaning through self-attention.
Right.
We covered how RAG pipelines gave those models an infinite external memory by plotting chunks of data in a 3D mathematical space. And finally, we're seeing how all of that culminates in the autonomous, tool-wielding, multi-day agents of today.
It really is an entire ecosystem of invisible mechanics working together.
And if you're building in this space, knowing how these pieces fit together is the difference between blindly paying API fees to a cloud provider and actually engineering an intelligent system.
Which, if we can pivot for just a second, brings us to a really compelling, almost philosophical shift happening right now.
Let's hear it.
We've spent this entire deep dive talking about cloud providers, API costs, and token economics. But there is a massive parallel movement happening right now in open source local AI.
Oh, like using tools like Llama or Llama.cpp?
Exactly, because normally a massive 70 billion parameter model requires a literal supercomputer to run, but developers are using a technique called quantization to shrink them down.
Quantization, how does that work?
It's fascinating. A neural network's weights are typically stored as highly precise long decimal numbers. Quantization essentially chops off the long tails of those decimals, converting them into smaller, lower precision numbers.
Oh, it's like taking a massive uncompressed raw photograph and converting it into a slightly lower resolution JPEG.
That's a perfect analogy. You lose a tiny fraction of the crisp detail, but the file size shrinks so drastically that you can suddenly fit it on your phone. By compressing these models down to, say, 4-bit quantization, you can run a genius-level AI entirely locally on a standard laptop with just 35 gigabytes of RAM.
That is insane.
And that unlocks the concept of compute sovereignty. Think about it. If tokens are the new currency of thought, and ours is how we give machines a long-term memory who ultimately owns that intelligence.
Right now, the cloud providers do.
Exactly. When we rely solely on cloud APIs, we are essentially renting a digital brain. Every query, every private document we upload is processed on someone else's server, and we pay a toll for every thought it generates.
We're leasing our own digital cognition.
But with local AI, you own the engine. Imagine a localized RAG pipeline containing your private financial records, your unreleased code, your personal journals, everything, and it's processed entirely on the hardware sitting on your desk.
No subscription fees, no data leaving your house, no safety classifiers artificially degrading your output.
That completely flips the power dynamic of the whole industry. What happens to the knowledge economy when every single person has an entirely private, locally hosted, genius-level brain that they own outright?
It democratizes the black box. We started this deep dive talking about how typing a prompt feels like magic. But as we've unpacked, it's not magic. It's tokens, attention weights, embeddings, and mathematical space. It is a highly mechanical engine.
A very powerful engine.
And the most exciting part, we are rapidly approaching the day where you don't have to rent that engine from a tech giant anymore. It might just belong entirely to you. Keep mulling that over. We'll catch you on the next deep dive.